Hello, everyone. My name is María de la Almudena Martín Gómez, and I'm a bachelor student based in Spain. I'm excited to present QuantumSat, which is an ambitious mission currently in the design and conceptual phase, motivated to advance in the fields of secure quantum encrypted communication using PocketQube 𝗖𝗍. While I'm still learning in this field, and I feel a little sick, to be honest, I will do my best to explain both the core concept and the mission in a way that is clear and easy to understand for everybody here. First of all, I would like to thank 𝗖cie Academy for the generous sponsorship and Alba Orbital for inviting me. As quantum computing continues to evolve, traditional encryption methods face increasing risks. This presents a major challenge for space-based communication, which handle sensitive governance, scientific, and commercial data. The mission QuantumSat aims to demonstrate quantum key distribution in space, paving the way for secure quantum networks. Traditional encryption relies on mathematical complexity, which quantum computers may soon break. Quantum key distribution offers a revolutionary solution, leveraging quantum mechanics to ensure secure encryption. If an eavesdropper attempts to intercept quantum keys, the laws of physics cause detectable disturbances, making interception impossible. What is quantum encryption? Quantum encryption is basically the same as quantum key distribution, a way to safely share encryption keys. What makes quantum key distribution special is the possibility to capture hackers thanks to the laws of physics. The importance of quantum key distribution in satellite communication. Here we have an unbreakable encryption. As I mentioned before, they are based on physical law rather than mathematical complexity, and that's why they are unbreakable encryption. They have unbreakable encryption. Long distance secure key exchange. It allows it with satellites because we can distribute quantum keys over vast distances, overcoming the limitation of fiber optic networks and enable global quantum secure communication. Finally, quantum key distribution provides stability for future networks. Basic on quantum computing in mechanics in computing. Let's look at the fundamental quantum properties and concepts that enable this technology. First of all, we have superposition that allow qubits to exist in multiple states at once, rather than being only in one state, like 0 or 1, like classical bits. Entanglement that creates a strong correlation between qubits enable instant state changes regardless of distances. And quantum interference that enhance the probability of correct answer while cancelling out incorrect ones, improving the computational efficiency. Also qubits that are the fundamental units in quantum information. Classical methods, as I mentioned before, like RSA, rely on complex mathematical problems. Quantum computers, using algorithms like source algorithms, can solve these problems exponentially faster. This puts at risk traditional encryption, making most current cryptographic methods obsolete once computing computers become more powerful. Quantum key distribution offers a secure encryption method resistant to quantum attack. Unlike classical encryption, quantum key distribution does not rely on computational complexity, but rather on the laws of physics, as I mentioned, to ensure security. Here I will talk a little bit more about the mission. First of all, there is a sender, which is a ground Q call that is based in China, that transmits quantum keys using wave coherent pulses over a quantum channel, which in this case is optical. Key measurement: the receiver, which is a PocketQube, measures the quantum state of the photons and stores the raw key. Eavesdropping detection: as mentioned before, any interception will be captured. And also there is classical communication. A separator F is used for error correction, key reconciliation, and privacy amplification to finalize the secret key. And also secure communication, the final quantum key is then used to encrypt and decrypt messages using a symmetric encryption scheme, in our case, one-time pad. And this combination of quantum channel and classical channel ensure secure encryption even against quantum computers. This is probably secure. As I mentioned before, quantum key distribution is secure because it is based in the laws of physics. It is essential for future security. With quantum computers on the horizon, quantum key distribution is the only known method to guarantee long-term security. And as I mentioned, eavesdropping is impossible. Now here I will talk a little bit about how quantum key distribution works for generating and distributing quantum keys. First of all, there is a photon preparation in which the sender, in our case the ground key, encodes quantum states using photons polarization. Then there is a quantum transmission. Photons travels through the quantum channel to the receiver. In our case, it is the PocketQube. And then there is a measurement in which the receiver measures the photon states using randomly chosen bases. And there is a shifting in which the sender and the receiver use classical channel to compare bases and discard the mismatches measurements. There is also key distribution here explained, in which there is error correction. The sender and the receiver correct discrepancies in their shared bits. Privacy amplification, in which they refine the key to remove any leak information. And a final key, the shared key that is established for secure communication. Well, as I mentioned, in addition to the quantum communication, it's necessary to establish a classical communication of non-secure information for the key exchange, and this will be performed using standard RF links. This is a quantum key distribution post-processing. The exchange quantum signal form a raw key, which is processed into a final shared key for encryption, and when combined with one-time pad encryption, quantum key provides information theoretic security, making it persistent to attacks even from quantum computers. One of the key challenges here is to choose between uplink and downlink communication, and each approach has its own advantages and disadvantages. Uplink, where the quantum signal is sent from the ground station to the satellites, experience higher losses due to atmospheric turbulence. As the beam propagated upwards, it encounters a wavefront aberration that causes significant beam spreading, reducing efficiency. However, a major advantage of uplink is that the light sources remain on the ground, making the satellite's payload a little bit easier to make rather than the other method that is the downlink. In the downlink, on the other hand, generally has lower losses because the beam first propagate through the vehicle and then before entering the atmosphere. This means less beam spreading and better overall transmission efficiency. However, the light source is on the satellites, which increases a lot the complexity in manufacturing. And now there are two pictures in which the first one in the left, we can see that the diffraction losses varies with the telescope separation and aperture size. And we can see that larger telescope diameters help to reduce losses, of course. And on the other one, we can see that diffraction losses at different altitudes, from LEO to GEO, and LEO satellites tend to experience lower losses due to shorter distances, while GEO satellites at much higher rates suffer greater losses. There are two different quantum key distribution protocols, which is the discrete variable 1 and the continuous variable 1. This is the protocol that we will be using, which is the BB84, and is one of the most widely used in quantum key distribution. And it consists in which the sender transmits photons that are randomly polarized in one of the two bases, and the receiver then measures these photons using randomly chosen bases. When the receiver selected basis matches the sender one, he correctly receives the bits. After the transmission, they compare their bases over the public channel, and they only keep the matching one to form a secure cryptographic key. One of the key strengths of BB84 is its ability to detect safe dropping. If a third party tries to intercept the quantum state, the act of measurement disturbs them due to the no-cloning theorem in quantum mechanics. This is the decoy state protocol that enhances BB84 quantum key distribution by preventing photon number splitting attacks, where an eavesdropper exploits multi-photon emissions to steal information and detect it. To counter this, sender randomly varies the intensity of laser pulses, missing normal signal pulses, and with weaker decoy pulses. Since an attacker cannot distinguish between them, any interception introduces detectable anomalies. Well, I will miss this. This is the mission concept and objectives. The QuantumSat mission aims to demonstrate and secure image transmission using quantum key distribution in a 2P PocketQube, and the satellites will receive quantum keys from the ground key station, which is the ground in Earth, in charge of creating the quantum key. Then the satellite will receive the quantum key from this ground key station and use them to encrypt onboard images and transmit them via S-band RF communication to a ground station. And this ensures highly secure data transmission, leveraging quantum mechanics to prevent eavesdropping. In addition to the quantum channel, a classical channel is also established for key reconciliation, authentication, and encrypted data transmission, ensuring the overall security and integrity of the communication process. Sorry. Here is a QuantumSat product. We can see that the different parts, the EPS, the battery, the camera, the pointing, the communication module, the OBC, and the payload. But I motivate you to go downstairs or upstairs, I don't remember, where you can find some posters, and there is one poster about all of this, and you can find the different components in more detail. These are the key scientific and technological goals. First of all, to demonstrate space-based quantum key distribution. to test the to increase quantum secure encryption in orbit, and to analyze environmental effects on quantum key distribution. And also there are some technological goals, such as integrate quantum key distribution into a 2P PocketQube, develop an optical pointing and alignment mechanisms, and demonstrate hybrid quantum and RF communication. And future implications, to scaling to do bigger quantum key distribution satellites, the role of PocketQubes in secure space networks, and potential for deep space quantum communication. And conclusion and next steps, QuantumSat aims to demonstrate the feasibility of quantum key distribution in ultra-small satellites. PocketQubes can play a crucial role in low-cost satellites in quantum key networks, and future missions could scale this technology to larger satellites and deep space. Future developments of possible consideration are further miniaturization of quantum communication hardware to improve efficiency in PocketQubes, developing intersatellite quantum links for secure constellation in LEO and far beyond, and collaborating with international space agencies, research institutions, and private companies to advance space-based quantum networks. And that's all. Thank you all for attending.